Welcome back to this next video in which we are discussing the parathyroid glands and vitamin D. Okay, so we're currently in the process of discussing how parathyroid hormone is actually going to achieve its effects on the kidneys. Okay, remember we said the two effects it's going to have on the kidneys are it's going to increase calcium resorption and decrease phosphate resorption. We've looked at how it's going to increase calcium resorption. Now what I want to have a look at is how it's going to decrease phosphate resorption. Okay, so firstly let's just study how phosphate is actually resorbed in the kidneys. So phosphate is filtered into the glomerular filtrate just like calcium. It's not a very big molecule, so it comes through as well. Okay, and most of it is going to be resorbed in the proximal convoluted tubule and a little bit in the distal convoluted tubule. So the fractions or percentages looks like so. So the proximal convoluted tubule is going to resorb 80% of the phosphate ions that are filtered into the glomerular filtrate, and the distal convoluted tubule is then going to resorb a further 10%. Okay, making it up to a total of 90% of the phosphate ions that are filtered into the glomerular filtrate are actually going to be resorbed. The other 10% is then going to be excreted into the urine. Okay, so what's going to happen then is parathyroid hormone is going to increase the amount that is actually going to end up in the urine. It's going to decrease the amount that we're actually going to resorb. So what we need to study is the mechanism by which proximal convoluted tubule cells and distal convoluted tubule cells actually resorb the phosphate ions, and then we need to have a look at how the parathyroid hormone is going to influence that. So resorption of phosphate ions is done completely transcellularly. So again, I'll draw a picture of a renal tubule cell here, and this could be a renal tubule cell of the proximal convoluted tubule or a renal tubule cell of the distal convoluted tubule. Okay, let's say this is the apical side, these are of course the tight junctions, and this is the basolateral side. Okay, so we're going to have a protein then on the apical side for transporting phosphate ions from the luminal fluid into the cytoplasm of the cell, and this crossing is well understood. The crossing for phosphate ions from the cytoplasm across the basolateral membrane into the basolateral fluid here is not so well understood, so I'm only going to be able to talk about what happens here. Okay, so here, how are we going to move phosphate ions into the cytoplasm of the cell? Well, this is done using the sodium gradient across the cell membrane. Okay, so we're going to have a transporter on the apical membrane then. So it's going to be localized specifically to the apical membrane of our renal tubule cells, and this is going to be a co-transporter for sodium ions and phosphate ions. So this is what's known as the sodium phosphate co-transporter. So the NAPI co-transporter is what it's called, and it's going to move sodium ions down their electrochemical gradient into the cytoplasm of the cell, and it's going to use that energy to move phosphate ions from the luminal fluid into the cytoplasm of the cell as well, and that gets those phosphate ions from the lumen into the cytoplasm of our renal tubule cell. Now, this is a very clever transporter because it's capable of transporting phosphate ions that are either in the hydrogen phosphate or the dihydrogen phosphate form. So remember, phosphate ions can have different forms, and depending on which form they're in, that will determine what their charge is. Okay? Now, for those different phosphate ions, dihydrogen phosphate and hydrogen phosphate, you're going to have to move differing numbers of sodium ions in. So let me explain this. So you can either transport the phosphate ion in the form HPO4 2-, which is hydrogen phosphate, i.e. where you've just got one proton and the other two oxygens are of alcohol, which were alcohol groups in phosphoric acid. They have lost their protons. You can transport that, but in that case you'll have to bring in 3 sodiums, okay, to provide the energy for moving that ion into the cytoplasm of the cell, or you can move the dihydrogen phosphate through. And remember, these are the two major forms that phosphate ions are actually in the blood, and therefore they'll be the two major forms that they're actually in this luminal fluid here. And the other one is H2PO4 minus here, the dihydrogen phosphate, and in that case, because the charge is slightly less, it's just 1 this time, you only have to move in 2 sodiums. So understand that the sodium phosphate cotransporter is capable of moving 2 different forms of phosphate, the hydrogen phosphate and the dihydrogen phosphate, but depending on which one it's moving, it will require a differing number of sodium ions to be moved down their electrochemical gradient with the phosphate ion to actually get it into the cytoplasm of the cell. Okay, so that's the sodium phosphate cotransporter, which will be localized to the apical membranes of these renal tubule cells of the proximal convoluted tubule and distal convoluted tubule. And this transports these phosphate ions, the main 2 types of phosphate ions, into the cytoplasm of our renal tubule cell. Then somehow the phosphate ions then get across the basolateral membrane, but the mechanism for that isn't known. Okay, but they do, and then of course they'll be in the basolateral fluid and they can return to the blood. Okay, so that's how we resorb phosphate ions in the proximal convoluted tubule and distal convoluted tubule, and it is a transcellular mechanism. Parathyroid hormone is once again acting through the parathyroid hormone 1 receptor, which is on the basolateral membrane of these renal tubule cells of the proximal convoluted tubule and distal convoluted tubule, okay, and is, once activated by parathyroid hormone, going to activate all sorts of intracellular signaling cascades. And these intracellular signaling cascades are going to lead to the inactivation of the phosphate resorption. So somehow they're going to inactivate this step here with the sodium phosphate cotransporter to reduce the amount of phosphate that we're bringing out of the lumen into the cytoplasm of our renal tubule cell. How are they going to do that? Well, what happens is these proteins here, these cotransporters, these sodium phosphate cotransporters, are removed from the apical membrane and sequestered into vesicles inside the cytoplasm of the renal tubule cell. So what's going to happen is you're going to endocytose these proteins and have them now in vesicles like so. So here is a vesicle with lots of these sodium phosphate cotransporters in. Okay, so here they are in orange. That is now inside the cytoplasm. So you're going to take your sodium phosphate cotransporters out of the apical membrane and instead store them in these storage vesicles inside the cytoplasm of the cell here. Okay, and obviously when they're in these storage vesicles, they're no longer capable of moving phosphate ions across the apical membrane from the lumen into the cytoplasm of the cell. So parathyroid hormone, acting through the parathyroid hormone 1 receptor, is going to hugely decrease the number of sodium phosphate cotransporters that are in the apical membrane of our renal tubule cells in the proximal convoluted tubule and in the distal convoluted tubule. Hence, the amount of phosphate that's actually going to be being resorbed by these cells is going to go down, so more phosphate will remain in the fluid in the lumen and will end up in the urine. Hence, phosphate excretion by the kidneys is going to go up, and you will end up with more phosphate in the urine, and that is known as phosphaturia. Okay, so parathyroid hormone acting on the kidneys is going to result in phosphaturia, and again, let me remind you of why this is a useful thing to do. It's because of the fact that we are trying to resurrect, or restore is a better word, we're trying to restore the free calcium ion concentration. That's the really important one that must not vary. Okay, if we want intracellular signaling not to be hugely disturbed, we need extracellular free calcium ion concentration to remain the same between 1.3 and 1.5 millimolar. We do not care about how many calcium ions are bound to phosphate ions. That isn't an important parameter to keep the same. Okay, so we're going to get rid of loads of phosphate ions from the blood, and all of the calcium that was previously bound to those phosphate ions is now going to become free calcium ions, and hence we're going to raise free calcium back up. Okay, which is more important than keeping the concentration of calcium phosphate in the blood the same. Okay, so there's how parathyroid hormone then is going to affect the kidneys to increase phosphate excretion. So far we've seen that parathyroid hormone will increase calcium resorption in the kidneys and decrease phosphate resorption in the kidneys. There's one final action that it's going to have on the kidneys, which is going to take a quite a bit of background knowledge to understand, and we're going to have a huge sort of diversion off to discuss this background. Parathyroid hormone is going to activate proximal convoluted tubule, renal tubule cells, to perform the final step in the activation of vitamin D, which is known as the 1-hydroxylation of vitamin D, to turn it into the active form of vitamin D, which is called 1,25-dihydroxyvitamin D. Okay, so parathyroid hormone is going to cause the kidneys to make the active form of vitamin D, to perform the final step in the reaction that makes the active form of vitamin D. And the active form of vitamin D is then going to go up in the bloodstream. And this active form of vitamin D, along with parathyroid hormone, are going to cause lots of effects. So in particular, both of them are going to work together to drive the bone to release calcium. And in addition, vitamin D, the active form of vitamin D, 1,25-dihydroxyvitamin D, is also going to go to the gastrointestinal tract and tell it to absorb more calcium next time we eat a meal, and also absorb more phosphate next time we eat a meal, whereas parathyroid hormone won't do that. So that's what I mean by saying parathyroid hormone indirectly affects the gastrointestinal tract by causing the creation of this active form of vitamin D. Now, to understand all of that, of course, we need to know something about vitamin D. So now what we're going to do is have a huge, great diversion where we're going to talk about vitamin D, and we're going to go through all of the different forms of vitamin D and the different levels of activation of vitamin D, so that it all makes sense. And then we'll come back and put it all together and talk about how parathyroid hormone and vitamin D together will affect the bone to bring up calcium level, and how vitamin D, the active form of vitamin D, will affect the gastrointestinal tract. So we'll have a break here, and in the next video we'll discuss vitamin D.